Hello everyone. Pretty lazy day today, right? So yes, we were discussing about Alpha and Boltzmann. We completed that, and then in the previous lecture, I told you I would start absolute zero scale of temperature and absolute zero. But since today I want to solve more of numerical problems relating to Charles law and Boyle's law, I would like to take up another topic which is called the ideal gas equation, which is basically a combination of Charles law and Boyle's law. We'll just first take up that small topic on ideal gas equation, and then we'll try to solve few numericals relating to the ideal gas equation. All right. So yes, ideal gas equation. So before we move on to ideal gas equation, what we should know about gases are there are basically two types of gases that has been classified according to their behavior. So what kind of behavior we are talking about is the behavior of gases relating to Boyle's law and Charles law. Let me tell you that although we have Boyle's law and Charles law, most of the gases do not follow Boyle's law and Charles law. They deviate from the Boyle's law and Charles law curve, and some of the gases which follow Boyle's law and Charles law does not really exist in the Earth's biosphere, right? So what are ideal gases? Ideal gases are gases that follow Boyle's law and Charles law completely. Okay, it's very difficult to find that kind of gas in our Earth's biosphere, and those gases which do not follow Charles law and Boyle's law are called the real gases. So you need to remember this. You might be asked, what do you mean by real and ideal gases? So uh, open your textbook, find the actual definition, or if not, then you can just uh, use the definition that I have given you. That is, gases which follow Charles law and Boyle's law completely are called. Okay, sorry, here I've written is called are called. Ideal gases, and then gases which do not follow Charles law and Boyle's law completely are called real gases. Okay? So having this knowledge, this particular equation we are dealing with the ideal gases. Real gases is a bit complicated. We will study only in higher standards, but ideal gases we can deal here in this standard itself. And uh, the equation that I'm going to show you is for ideal gas. It's written here, ideal gas equation, and it's not for real gases. So now what we can do is, since volume was varying inversely as pressure and directly to temperature when certain constants are kept in case of Charles law and Boyle's law, to obtain the ideal gas equation we'll combine, because both Charles law and Boyle's law needs to be followed. So let us come to a common ground, that is, let us combine the Charles law and Boyle's law, and then we see what we find. So we know that from Boyle's law, V is inversely proportional to pressure, and from Charles' law, V is directly proportional to pressure. I'm not going towards the exact uh, formula or the mathematical formulation of Charles' law, just a qualitative discussion. That is, V is directly proportional to T. Now, what we have is, after this is from principle of joint variation, since V is proportional to inversely proportional to P and directly proportional to T, we can write V is directly proportional to T by P when M is kept constant. Remember, the mass of a gas is always kept constant. Now, in this case, the temperature was constant, and in this case, the pressure was constant. Now, both of them are varying, temperature and pressure. Uh, Only the mass is constant. We need this ideal gas equation because if we use only Boyle's law, then the temperature has to remain constant, right? Temperature cannot change. And if we have to use Charles' law, pressure cannot change. So what happens when both pressure and temperature changes? We do not have an equation. So to obtain that equation, we combine these two laws, and let's see what we find out. This K here is the removal of this proportionality sign and replaced by equals to a constant. So this you know from the principle of joint variation. Now I multiply this P into V. What remains is K into T. So we have an equation called PV is equals to KT. This equation is called the ideal gas equation, or equation of state of a gas, or simply gas equation. So these are the three names: ideal gas equation, equation of state of a gas, or gas equation. PV is equals to KT. We'll try to modify, because K proportionality constant could be anything, so we'll just try to modify this K and introduce some easy constant by taking 1 gram mole of ideal gas. If we take 1 gram mole, well, you know what moles are. So if you take 1 gram mole of ideal gas, this K has to be replaced by R. Okay, and this R is called the universal gas constant, or simply gas constant. It has a value of 8.314 joule per Kelvin, 8.314 joule per Kelvin, yeah, per mole. So our new equation has become PV is equals to RT, right? Now that is for 1 gram mole of ideal gas. What if there are n gram mole? There are more than 1 gram mole. Then we'll, for n gram mole, n could be anything, 2, 3, 4, 5, 6, 7, 8, 9, 10, could be any number. So for n gram moles of ideal gas, the equation will become PV is equals to nRT. You just have to multiply that n in the right hand side, right? So this equation is very important here. PV is equals to nRT, or PV is equals to KT for qualitative discussions. If we have to solve numerical problems, that we have to have a different equation, because just one equation, it's very difficult here. So to have some working formula for solving numerical problems, we will move on to another derivation. Now for that derivation, we'll assume some of the parameters. Let's say the initial temperature T1 Kelvin. Remember, this temperature is in Kelvin here, right? This temperature is in Kelvin here. I've taken that as Kelvin here. So at temperature T1 Kelvin, the volume is V1 and P1. Now as the temperature is increased to T2, volume and pressure becomes V2 and P2. So see here, none of temperature and pressure are constant. All pressure, temperature, and volume are changing. We cannot use exclusively Charles law or exclusively Boyle's law here in this case, because both temperature and pressure are changing. So what we can do is, we can use the gas equation for initial condition, that is when the temperature is T1, P1 V1 is equals to RT1. Just using this equation, PV is equals to RT. Okay, so, and for the second equation, a second condition, it is P2 V2 is equals to RT2, right? Now if we divide equation 1 by equation 2, what we get is P1 V1 by P2 V2 is equals to RT1 by RT2. You see here, R gets cancelled now. What we get is P1 V1 by P2 V2 is equals to T1 by T2. Just rearranging, we'll take this one initial condition one side and final condition on another side. That is T1 in the denominator of P1 V1 and P2 in the numerator of T2. What we finally get is P1 V1 by T1 is equals to P2 V2 by T2. This is also called the gas equation. This is the working formula of the gas equation. This is used in most of the numericals that we going to solve. Actually, we've already solved some numerical problems using this formula, but you did not know what this formula was back then. Now we'll try to solve this formula, or solve numericals following this formula. So this formula is very important, examination point of view as well as your understanding point of view. If you take up science, it's very important later on to convert any pressure and volume at any temperature to the STP. We've already done the conversion of any uh, pressure volume into STP pressure volume, right? So now, since we have this formula, let us try and solve this numerical problem, uh, which is fairly easy. So the question says 87 cc of moist nitrogen gas is measured at 9. This moist we need not be here. Just ignore this. 87 cc of nitrogen gas is measured at 9 degrees Celsius. Remember the Celsius, okay? You have to convert it to Kelvin. And 659 mm of Hg pressure. Okay, so our V1 is given, T1 is given, and P1 is given. Find the volume of nitrogen at STP. We have to find V2 using 0 degree Celsius T2 and 760 mm of Hg as your P2. So remember that you cannot use 0 degrees Celsius here. Again, you'll have to convert this to Kelvin. Temperature is in Kelvin. I have written capital T. Always remember capital T means Kelvin. Small t, if I had tried, that means degrees Celsius. So I request you all to solve this problem yourself and then let me know the answer in our chat room. So thank you. We'll meet up again tomorrow with the next interesting lecture.